In an introduction to conditional probability, we introduced some formulas. Now we're going to introduce independent events. Two events are called independent events when the occurrence of one of the events doesn't affect the probability of the occurrence of the other event. Two events A and B are independent when the conditional probability of B given A is equal to probability B. It means that probability of A has no impact on probability of event B, or when the conditional probability of A given B is exactly the probability of A. So basically saying that two events are independent from each other if you find their conditional probability, the probability of A given B, and as we remember the formula, it is the probability of A intersection B divided by the probability of B. On the numerator, their intersection becomes their multiplication, probability of A times probability of B, and then you can divide it by probability of B. You can cancel these two out. That's how you get the conditional probability of A given B is equal to probability of A. And if you find the conditional probability of B given A, as you remember the formula, it is their intersection divided by the condition down here. But if they are independent from each other, they have the probability of A intersection B as the probability of A times probability of B divided by probability of A. You can cancel out the common factor and you end up with probability of B itself. Take a look at this example. Driving over 85 miles per hour, which is event A, and then getting in a car accident B. Are these two dependent or independent? Well, driving over 85 miles per hour increases the chance. So it has some impact on getting into accidents. So these two events are dependent. The multiplication rule for the probability of A intersection B. The definition of conditional probability gives us the following result. Remember that if you have the probability of A given B, this defines as the probability of A intersection B divided by the probability of B. So if you multiply both sides by probability of B, you end up with the probability of A intersection B equals to conditional probability of A given B times the probability of B. This is the multiplication rule for the intersection. The probability that two events A and B will occur in sequence is the probability of A and B. So remember that and intersection, they have the same meaning, which is equal to the probability of A times the conditional probability of B given A. If events A and B are independent from each other, as we saw before, then the rule can be simplified. The probability of A and B, which is the probability of their intersection, equals to probability of A times probability of B. An important theorem that is called Bayes' theorem. Suppose A1, A2, A3, AK be a collection of K mutually disjoint events. Suppose you know the probability of these events as well, P of A sub I. Then for any other event like B, given that probability of B is positive, it means that it can be on the denominator, then the probability of A sub J given the condition B can happen as the probability of A sub J given B as the probability of A sub J intersection B divided by the given condition. We can write this as the probability of B given AJ times the probability of AJ, this is the multiplication rule that we just learned, divided by the summation of the conditional probability of B given AI times the probability of AI, and I starts for 1 and goes to K. So this is basically the Bayes theorem. Now that we learned Bayes theorem, let us take a look at this example. Incident of a rare disease. Only 1 in 1,000 adults is affiliated with a rare disease for which a diagnostic test has been developed. The test is such that when an individual actually has the disease, a positive result will occur 99% of the time. Whereas an individual without the disease will show a positive test result only 2% of the time. If a randomly selected individual is tested and the result is positive, what is the probability that the individual has the disease? Okay, let us take a look at our 3 here. To use Bayes' theorem, let A1 be the set of individuals that has the disease. A1 has the disease and A2 doesn't have the disease. Then you either have a positive test or its complement, which is a negative test. If the person doesn't have the disease, you have 2 possibilities as well. You either have a positive test or its complement that is a negative test. Then you can find the probability of their intersection as well. So the probability that the person has the disease is 0.001, 1 in 1,000. And the probability that the person doesn't have the disease is 0.999, 1 minus 1 over 1,000. Then, if the person has the disease, the probability that this is positive is 99%, negative test 1%, and then if the person doesn't have the disease, the possibility that the test is positive is 2%, and the complement is 98%. Very good. So A2, as we mentioned, is the set of individual doesn't have the disease, and B, as we mentioned, is the set of positive test result. Then we know that P of A1, the probability of A1 is 1 out of 1,000, so 0.001, and the probability of A2 is 0.999, 1 minus 1 over 1,000. The probability of B given A1 is 99%. So take a look. The probability of B, so we are connecting these two. On the first line, the probability of B given A1 and the probability of B given A2. So these are the lines that we are following here, everyone. And then note that the probability of A1 has the disease, and B, the positive test, is going to be following the conditional probability, that is the probability of A1 and B divided by probability of B. But the probability of A1 and B is going to be 0.00099 divided by the probability of B, which is 0.02097. Why is that? Because to calculate the probability of B, we are following the Bayes' theorem. On the denominator, take a look. You have the summation of probability of B given A1 times probability of A1 plus the probability of B given A2 times A2 as you can see just right here. If you add these together, you get the probability of B, which is 0.02097. This goes on our denominator here.